It's our pleasure to welcome today at stage Kun Wan, who recently joined the department as assistant professor, right, in September. So welcome. This is, as you know, this series of seminars that we organize for our junior professors, or people joining the department, so that we can get to know what they are doing, and eventually foster collaborations, right, and find synergies. So Dr. Wang, he holds a PhD degree in aerospace engineering from Cheonan University in China in 2025, and he was a visiting scholar at the University of Auckland, New Zealand in 2024. His research focuses on nonlinear guidance and control for autonomous vehicles, optimal control, applied to space, GSC in space, but not only. I guess you have other interests. And well, today he's going to be talking about convergence and on unicycle vehicles, right? Or unicycle movement. Okay, so floor is yours. Thank you very much.
Thank you very much. And thank you for coming. And my talk is guaranteeing convergence in trajectory shaping guidance for arrival time constrained unicycle vehicles. And in this seminar, I will mainly talk about my recent work. So this seminar is divided 4 parts. The first is background. The second is state of the art. And the third part is a new novel framework providing guaranteed convergence. And the last is the conclusions and future work. So what is a unicycle vehicle? It's the simplest kinematic model widely used to represent a non-holonomic mobile robot moving on a 2-dimensional plane. And it's also a fundamental model for understanding navigation, guidance, path planning, and so many other things in robotics and aerospace engineering. So this picture shows the frame for UAV's planar motion. And so we have the state vector. It includes the position, x, y, and the heading angle, theta. In this frame, the lambda is the line of sight angle, and the sigma is, we usually call it the look angle. And the control inputs, we have the linear velocity and the angular velocity. And the angular velocity, A, is perpendicular to the velocity vector. And we also have the kinematic equations written in matrix form. And for this kinematics, we have a non-holonomic constraint. It means that the vehicle cannot slide sideways. Imagine that you are driving a car and you need to do a parallel parking. To do it, you must first go forward and go backward. You cannot just slide sideways to your parking spots. So this model is equivalent to several platforms, such as differential drive robots, automated guided vehicles, and especially for fixed-wing UAVs. When flying at a constant altitude with a constant speed, that means the velocity does not change. This model becomes the Lubin's vehicle, which is widely used for aircraft trajectory planning. So why do we need to control the arrival time of fixed-wing vehicles? Here are some examples. The first is coordinated multi-UAV observation. It means that multiple UAVs are deployed from different locations to monitor a specific area of interest. The second example is moving platform recovery. In such a scenario, a UAV needs to land on a moving ship or a ground vehicle. The third example is intelligent swarm cooperative control. It means that a group of autonomous UAVs, they must quickly transition from a searching pattern to a tracking formation around a dynamic asset. So right now we come to the mathematical problem formulation. So the objective is to design a guidance law for the lateral acceleration to steer the UAV from the initial condition to a target position at a pre-specified final time. It means that the final time is fixed. Therefore, we have the kinematics, and we also have the boundary conditions. If this problem can be solved in real time, the guidance law, it can be updated every guidance cycle to handle speed disturbance and environmental uncertainties. Therefore, we make a assumption that the UAV is flying with a constant speed. And right now, we will also ignore the control acceleration constraints. So this work can be traced back to 2006. There are plenty of works since then. So some representative methods include linear optimal control, nonlinear control, trajectory shaping, which is one of our topics today, and machine learning. So linear optimal control to solve this problem is linearize the kinematics around the nominal trajectory, and therefore the time to go. It means the remaining flight time before reach the target can be estimated in closed form. Therefore, we can formulate a linear quadratic optimal control problem to minimize the control effort. The control effort is related to something like energy consumption. So the advantages include they have closed form solutions for linear optimal guidance laws, and therefore it's computational efficient for real-time applications. Of course, there are some limitations. The first is it has to estimate the time to go, but the time to go becomes very inaccurate for large hitting areas. By this, I mean the trajectory is highly curved. And the second limitation is that the convergence is not guaranteed for all possible initial conditions. So the second method is linear control, such as sliding mode control or Lyapunov theory. Within this framework, the time to go error is enforced to converge to zero before reaching the target. Therefore, the arrival time can be controlled. The advantages include they also have closed form solutions, and the guidance law is nonlinear and is computational efficient. And the limitations is that they still rely on the time to go estimation, and the required control efforts, also the energy consumption may be very high, and convergence is also not guaranteed for all possible initial conditions. And the third method is trajectory shaping. Within this framework, the state or the control trajectory is parameterized as a function of time or other states, and the guidance problem is transformed into finding the guidance gain by solving some nonlinear equations. By this, we can just incorporate all the boundary conditions into trajectory shaping. And therefore, all we need to do is to solve some nonlinear equations, which can be solved by Newton's method. The advantages include there's no need for linearization or estimation of time to go, making it applicable to highly nonlinear systems, even for low-thrust spacecraft maneuvers. And there are some limitations. So the first is solving the resulting nonlinear equations may lead to multiple solutions depending on initial guesses, because with different initial guesses, the solution might converge to different solutions. And of course, the convergence is not guaranteed for all possible initial conditions. So here's an example of trajectory shaping, the Apollo guidance. So the guidance command is written as a polynomial function. And the last part is machine learning. So for machine learning, we usually have two methods. The first is supervised learning, and the second is reinforcement learning. For the supervised learning, it basically needs to solve a lot of nonlinear optimal control problems offline, and after that, we can get a training data set, and we can just use neural network to approximate the nonlinear mapping from the state to the optimal control solution. And after the training, the guidance command can be generated in real time. So the advantages include there's also no need for linearization, and we have real-time nonlinear guidance law, and they have high robustness to uncertainties and disturbance. And of course, there are also some limitations. The first is lack of interpretability, and the second is also the convergence is not guaranteed for all possible initial conditions. So after covering all the existing methods, we can conclude that right now there's no convergence guaranteed guidance law, despite this problem has been studied for nearly 20 years. And also, whether the arrival time constraint mission can be accomplished cannot be validated a priori. It means that because we have to assign an arrival time, but we don't know if the arrival time can be achieved before running any simulation. So this causes potential mission failures in practice. So to address this critical issue, after we will talk about a novel framework that guarantees convergence for all possible initial conditions. So before going into the details, we need to do some recaps. The first is, so we have talked about the guidance objective, and so here's an example. So a UAV is flying at a constant speed, and we also have the initial conditions. And the guidance objective is to guide the UAV to arrive at the target position, let's say at the origin, at some fixed final time. Let's say the final time is equal to 110 seconds. So in the literature, it's okay to say that as long as the final time is greater than, in such scenario, is 100 seconds. So actually that's not the case, and we will talk about it a little bit later. So we have two questions. So the first is, can the UAV arrive at the target at a specified time? The second, if yes, how to design the guidance law with guaranteed convergence? So here's a picture of the UAV's motion in Cartesian coordinated frame, and we can write it into the polar coordinate frame. And because the UAV is flying at constant speed, we can just normalize it to 1. So therefore, we have the kinematics, and we also have the boundary conditions. So in practical applications, the information of the range R and sigma look angle is from the navigation system. So this is from a work done by Taken. So she wrote the look angle as a cubic polynomial, And it's clear that with this, with equation 5, the boundary conditions on the sigma can be satisfied. And equation 6, because we have the r dot is equal to minus cosine sigma, and by doing the integration, this equation 6 will ensure that the vehicle arrives at the target at the specified time tf. So right now the nonlinear guidance problem becomes to solve equation 6. So it's a route finding problem. Actually, it's not easy. So here's a picture that shows the initial conditions, sigma naught, and also we have the guidance gain. And the z-axis is the value of the integral in equation 6. So because we need to solve this equation, so here are there are 3 planes. So that means r naught is equal to 0.5, r naught is equal to 1, and r naught is equal to 1.5. So from this figure, we can see that there are multiple solutions, and in some cases there are no solution. So that's the problem. So this is also from my previous work. So we derived some additional optimalities based on the geometric properties of the optimal trajectory. So for optimal control, we can use punctual gain minimum principle or KKT conditions, but they are all necessary conditions. So by analyzing the geometric properties, we have some properties such as symmetry and scalability, and the last is an additional geometric optimality condition. So the first property, it means that the trajectory are symmetric. So let's say the UAV starts from point A and it needs to arrive at the origin, and we can see that this trajectory and this trajectory, they are symmetric. Therefore, we only need to consider one scenario. The second is that because we have the constant speed assumption, we can scale the trajectory. So therefore, we can just fix the final time TF to 1. And the third one means that an extremal solution is obtained from the punctual gain minimum principle, which gives the necessary conditions for optimality. But with this, we found that the extremal solution, if sigma changes the sign at this time interval, the solution loses optimality. So it means that if we start from point B and the UAV flies along this trajectory is not optimal, even though the trajectory is based on punctual gain minimum principle. So with that, we will talk about the main results. So we just talk about 3 properties, and they are very, very helpful to derive a new guidance law. Although the 3 geometrical properties, they are derived based on punctual gain minimum principle and geometric analysis, they apply to any feasible solution. So the left shows the original problem. We have the kinematics and we have the boundary conditions. So the right shows a new guidance problem. So of course the kinematics, they don't change, they remain the same. And for the boundary conditions, right now because of the scalability property, we can just fix the final time TF to 1. So therefore, the boundary conditions are changed. And also, because of the symmetric property, we can just consider the initial condition for the look angle, because the original, the look angle can take values from minus pi to pi, and right now we only need to consider from 0 and pi. And so the third, we have a path constraint. It means that the look angle cannot change its sign. So so right now we formulate a new look angle shaping. So in equation 9, and so it's clear that this equation it satisfies the boundary conditions on the look angle. And we now the nonlinear guidance problem becomes to solving equation 10. So to ensure the constraint, the sigma cannot change its sign, we must make sure that the guidance gain satisfies the following condition. So with this, we have bounds on the guidance gain. So here's a picture that shows the integral of this. We have the g of the guidance gain kappa and the initial conditions sigma naught. So to solve this equation from this figure, we can see it's also not easy to solve this problem, right? So let's say we set the R naught to 0.5. So we draw a plane like this. We can see it also has multiple solutions. So we need to dig more. So we just derived the guidance. We just derived the bounds on the guidance gain from this figure. We can say that this is the lower bound on the guidance gain, and this is the upper bound. So from this figure, we can say that the problem becomes much easier, right? And also we need to consider another constraint. That's the initial distance, R naught. R naught, it cannot be negative, right? So R naught should be greater than 0 and less than 1. So with that, we can draw a figure. So this is the lower bound on the guidance gain, and this is the upper bound. And this plane is to show when this function g is equal to 0. And because we have to solve the equation g equals to R naught, because R naught must be positive. So therefore, we can see that the guidance gain, it has a narrower bound. So the guidance gain must be less than this curve. So with this, we can say that if the guidance gain take values, the lower bound and this bound, the solution will be suboptimal because the look angle does not change its sign. So right now we have a smaller bound. And also from this figure, we can see that the R naught also has some limitations. So here's the theorem that gives the condition for the UAV employing the proposed guidance law to arrive at the target precisely at TF is equal to 1. So the proof is quite easy. So because from this figure, we can see that g, the function, is normatically decreasing with respect to the guidance gain kappa. And the maximum, Gmax, is obtained at kappa equals to minus sigma 0. So we can see, so the maximum of this function, it is obtained at kappa is equal to minus kappa 0. So therefore, we have the equations. So as a result of theorem 2, for a UAV with an initial condition, so R naught prime, the prime means the actual flight speed, because when deriving the equations, we use the consumption that the constant speed is equal to 1. So therefore, we have the bounds on the achievable arrival time. So it means that the arrival time you want to achieve must be greater than this value. So back to the example before, we can see that the achievable arrival time is actually greater than 134 seconds. So if you assign an arrival time of 110, the mission will be not successful. So right now, the guidance problem becomes to solve a route finding problem. And when using Newton's method, the initial guess is also very important. Because we also have the lower bounds and the upper bounds, we can use the bisection method to solve this problem. But it only has linear convergence, so therefore we use a Newton's method to achieve superlinear convergence. So we use a quadratic approximation of the integral. We derive this equation. And so the guidance gain, kappa, it's actually a quadratic equation. So if the initial conditions they satisfy, they are in the achievable set A, then we can conclude that the discriminant delta is strictly positive. That means the equation 16 admits two distinct real roots. And with very simple manipulation, we now give the initial guess of the guidance gain. So it's written in equation 19. So here's the picture. So this plane is the initial guess for the guidance gain, and this is the actual guidance gain plane. So we can say that the initial guess is very close to the actual solution. Now we'll talk about some numerical simulations. So we conducted 10,000 initial conditions. So this is because we derived the achievable arrival time. So therefore, it's not a square. Instead, it's like a trapezoid. So all conditions converged, and the average number of iterations is less than 3. And the computational time, it's only 16 microseconds, which is far less than the guidance cycle. So therefore, the proposed method can be applied on board. So this shows the comparison with state-of-the-art methods. So with different methods, we have achieved different control efforts. And it's worth noting that the proposed method achieved a control effort. And GPUBs, when using GPUBs, we obtained 2 solutions. So it's clear that the proposed method can lead to suboptimal solution, and it's generated in real time. So this is another example. So this is a scenario when you need a UAV, like it has to wait for other UAVs. So therefore, the arrival time is very long, and we can say that to satisfy the arrival time constraint, the UAV takes a highly curved detour to satisfy the arrival time constraint. And to the best of my knowledge, so for this guidance problem, the proposed method is the only one available. So right now, I'll come to conclusions and future work. So a novel framework combining the optimal control theory and the trajectory shaping guidance to design arrival time constraint nonlinear guidance with guaranteed convergence. And the analytic bounds on the achievable arrival time is written in series form, allowing to check the feasibility of the mission a priori, means that we don't need to run any simulations. And also, an efficient algorithm is developed. And the performance is close to the nonlinear optimal control solution, but it requires significantly less computational effort. So this is another work. Actually, I just finished this work yesterday. So in actual scenarios, since the onboard sensor is typically strapped on or has limited gimbal, maintaining the target with the field of view is necessary for continuous observability. So in this figure, it means that this is the target and this is the UAV. To maintain that the target is inside of the UAV, so its look angle will be constrained. Otherwise, the UAV will lose the target. So therefore, we have another state constraint for this guidance problem. So this is a new shaping function. It use trigonometric functions to satisfy the look angle constraint. And so here's the video. So we have 3 UAVs. They start at a different initial position, and they are also flying at different speeds. And to make sure that the target is within the UAV's field of view, we have the look angle constraint. And the objective is to guide 3 UAVs to achieve a formation generation that you can see they arrive at a triangle at the same time. So it's clear that the look angle constraint is satisfied, and all the guidance commands, they are generated in real time. So another future work is to conduct real-world experiments. So this is the basic idea to apply the proposed method to real-world experiments. So first, we need to assign the arrival time to the guidance system. The delta t, it means the time step for the guidance cycle. So we need to use band to turn to achieve the the natural acceleration command. So this this Friday I will go to University of Granada and talk about the real world experiments there. And also there's another interesting problem. So this problem was studied by Euler. So it's in 1744. So this problem is also called Euler elastic problem. So the goal is to find the control that minimizing the control effort. So this problem is highly nonlinear and highly non-convex, and also all the states are fully constrained. So this problem is fundamentally important in robotics, solid mechanics, aerospace engineering, and biophysics. But to date, closed form solutions are only available for very special cases. So my idea is to extend the proposed framework, that is to use the insights from the optimal control theory to derive the suboptimal solution, because obtaining the optimal solution is extremely challenging. Hopefully with guaranteed or high convergence for this problem. Thank you very much for your attention.
Thank you. Thanks for your presentation. Are there questions in the audience? Okay, Berat.
Okay, can you hear me? Okay, hi, Kun. Thanks for the presentation. I had a couple of questions. If you go to slide 30.
30?
Yes. Yeah, I was wondering if you could tell us a bit more on how you came up with the profile in equation 9. Like that's something that you designed, no? Like a profile that you.
Yeah. So because when shape the look angle, it should satisfy the boundary conditions. So
sorry, you need. I think they are telling you to.
So right here we have the boundary condition on the look angle.
Oh.
So we have the sigma naught is equal to sigma naught, and at the final time, sigma 1 is equal to should also be equal to 0, and so with this equation, the two boundary conditions are naturally satisfied.
Okay, thanks. I think they're asking you to move closer to the podium, so.
Close.
No.
Speak by the microphone.
Yes.
Okay.
Okay, thanks. And is there any like a physical or geometric meaning to the profile, or
no?
No. Okay.
There's no physical meaning because actually, so its order is so this function is a cubic polynomial, and it's very simple. And so actually, it's from the previous work done by Taken, and so in this work, it's showing that sometimes the solution is very close to the optimal solution. So therefore, I still use the cubic polynomial for this problem.
Okay, thanks. And a second question about the time. So you're assuming that we have a specified TF final time. I was wondering if, like as sort of an extension, we could treat that as another variable. Like we could allow for variable time and treat that as another.
Yeah. So that's another scenario. That's like multiple UAVs. They have to communicate with each other to synchronize the arrival time. So right now, my work does not consider the communication among different UAVs. So there is no communication among different UAVs, and if they have communication, they can change the final time and to synchronize it.
And so, like for instance, halfway through your trajectory, if you update the time, can you still use the same trajectory, like the same shape, or do you need to update the shape as well?
Yes. So as long as the UAV is flying at constant speed, so we can use the scalability property. So because with this, we can scale the final time or the range. So therefore, even though the time is a variable, the proposed method is still applicable.
Okay, great. Thanks, Greg.
I can have a question. I can see that you are looking to optimize the time to get there based on control effort. But how easy it is your framework to add constraint like related to the engine dynamics, the atmospherics, and things like that? I'm thinking much more in one of the slides that you saw like a vehicle landing on a planet. And over there, typically what we use is the G-fold convexification because they allow to approximate at least some of the dynamics.
You mean like this figure?
It could be like this. So in your case, I didn't see how you were incorporating things like the engine dynamics, wind patterns, and things like that. So
Okay.
it's so fast the algorithm that it looks to me that is simplified in the posing of the problem essentially.
Yeah. Thank you very much for your question. So this work is just focused on the guidance problem. And for the dynamics, to include the dynamics and all the other things, we also have to consider the control loop. So right now, the guidance and the control loop is entirely separated. So that should be in this figure. So to consider the UAV's dynamics and all the other things such as actuators and something like engine, some stuff like that. So as long as the computation needed to generate the guidance command is less than the guidance cycle, it means that the guidance command can be updated during every guidance cycle. So therefore, if we consider UAV dynamics and other things, so I think as long as the speed, the flying speed, does not change a lot, I think we can still get good results. I hope that answers your question.
Thank you very much for your presentation. I have one question regarding multiple UAVs. So could you move to that slide?
UAV kinematics?
Yes. No, multiple UAV in your future works.
Okay.
So how did you come up with the guidance profiles for the 3 UAVs? So you consider them together in the framework of the optimization, or you drive the guidance separately?
I'm sorry, can you?
So did you consider, for example, conflicts between these trajectories? So you consider all the 3 UAV guidance in separate steps or at once?
So they are separated.
Okay.
So all 3 vehicles, they are separated, and they don't need to consider other UAVs motion. And so for this problem, I just assign the target position for each UAV, and I assign an arrival time for them to arrive their target position at the same time.
Okay.
And there is no communication among the UAVs.
Okay. But you think your framework can accommodate that? So considering the 3 or more UAVs together to also guaranteeing not having conflicts, for example.
So because the guidance for each UAV is entirely separated, so it does not matter how many UAVs you have. So yeah, so I guess the second question is to consider the communication, right? To adjust the arrival time.
Yeah, so because now the initial position of them are selected such that we don't see any conflict, but what if they
Yeah, so that will be like collision avoidance, right?
Yes, something in that direction. Because then you need to combine the dynamics and derivation of the optimal guidance a bit. I don't know, with this shaping framework, you can guarantee that?
So to consider the collision avoidance is quite challenging, especially when you need to generate the guidance command in real time. And also, I think if the collision is static, it means that collision is fixed. I think it will not be complicated for the proposed method. But if the collisions they move dynamically, then dynamically, I think that will be a great challenge.
Okay, thank you.
All right, I'm going to take the last one, if I may. Can you go to slide 40, please, where you are comparing the solutions of different methods?
40. Okay.
Yeah, something like that. Yeah, I was wondering if you have solved the problem using analytical optimal control, solving Euler-Lagrange equations, because I have the feeling that this problem is solvable.
Yes, it is solvable, but you cannot solve it in real time. So
Are you sure?
Yeah, I'm sure. So if you use the punctuality minimum principle, you need to generate the initial guess for the code states, which is very challenging because they don't have any physical meaning. And if you use the nonlinear programming, so like the GPOPs, and so all the conditions, they are just based on like for the nonlinear programming, they are based on KKT conditions. That's just necessary conditions for optimality.
Yeah, but that's numerical optimal control. But when it comes to analytical optimal control, you end up with a set of differential algebraic equations.
Yes.
That you can solve.
But you
need to solve for the co-states, and there is no physical meaning for
Yeah.
that, and that might be you might need to find an heuristics, but in principle you have a sort of closed for solution, or well, you need to integrate that numerically, but
yeah.
Well, I would at least try because I have the feeling that the problem is solvable using that approach as well. And maybe you can compare, and I don't know in terms of computational efficiency, but I have the feeling that it's solvable.
I think I also have the code in my laptop, and it's based on the indirect shooting method. And when you use that, sometimes you will get very strange solutions.
Okay, but then the problem is that on the numerical approach to solve the resulting set of equations. Okay. Good. Thank you.
Okay, thank you.
So I think we can close the session, right? Okay, thank you.
Okay.